Okay, stats, let's take a look at 9.2. A quick note, we've been using the z-table, but there's more stuff in that packet besides the z-table. The page after the z-table is what we call a t-table, and we're going to talk more about that as we go. A t-table is what we're going to use if our population sample is too small to be normal, so we can't use the z-table if it's not normal. Let's talk about a point estimate. Point estimate is the value of statistics that estimates the value of a parameter. For example, x bar can represent mu. Listed below are brain volumes of subjects used in a study. Treat the data as a simple random sample. Estimate the population mean. Okay, again, so if we have a bunch of data, here we have 10 brain volumes, centimeters cubed. How do we find the average of our sample? We simply add them all together and divide by 10. So you can take these in the calculator, divide by 10, you get 1130.2. So x bar is used to approximate mu, so the point estimate for mu is again going to be 1130.2. That's what we're estimating. However, just like in 9.1, in the proportion estimate, every sample we take will give us a different estimate because we get 10 different brains, so it may be a different value. So just like in the last section, we're going to need a confidence interval to help us figure out how sure we are if we are going to figure out if our estimation is accurate or not. So a t-distribution. So suppose a simple random sample of size n is taken from a population. If the population for which the sample is drawn follows a normal distribution, the distribution t equals x bar minus mu over, I'm kind of put this in parentheses, standard deviation divided by the square root of n follows students' t-distribution with n minus 1 degrees of freedom where x bar is the sample mean and s is the sample standard deviation. Okay, so on your t-table, across the top, you should have an alpha that deals with how accurate your confidence interval wants to be. Down the left, it'll tell you your degrees of freedom, and that's however many things you have in your sample minus 1. So the important part is you're going to have to practice reading it. So when you're given a certain sample size, you subtract 1 to get your degrees of freedom. And your confidence interval, that's where you look across the top. So it reads differently than the z-table reads. So just be aware of that. So what are some of the properties of the t-distribution? So this is the first time we've worked with it. The t-distribution is different for different degrees of freedom. The larger your sample size is, the closer and closer it gets to the z-score table because it gets closer to being normal. The t-distribution is centered at 0 and symmetric, just like the z-score. The area under the curve is 1, just like z-score. As t increases without bound, the graph approaches whenever equals 0. So it has almost all the same properties as z, but because you don't have enough samples, usually there's a little bit more in the tails than the z-distribution. Again, and if you look down at the bottom of the t-table with like thousands of samples, you'll notice that the numbers are almost identical to the z-table. Now again, a reminder. In the t-table, the numbers inside the t-tables are t-values, not area. So they're critical values. It's not the area to the left, it is the critical value you'll use for calculations. And in the t-table, the areas are at the top of the table represent the area to the right. So normally we look at areas to the left, but these are alphas to the right. So if you have a 95% confidence interval, that means you have 0.025 to the right. So the notation T alpha is the T value such that the area under the standard normal curve to the right is alpha. Okay, so let's practice just looking at the table. Find the t value such that the area under the t distribution to the right of the t value is 0.2 with 10 degrees of freedom. So your degrees of freedom are your row. So you look up and down on the left side, find your 10 degrees of freedom. Column is your area to the right. This is where we're going to be looking at for 0.2 as the area to the right. So when I see where those two line up together, I should find 0.8 0.879 in my t-table. What that means is at 0.879 standard deviations to the right, 20% of the data still remains on the right after I've gone up 0.879 standard deviations. That's the equivalent of, in the last section, of the z alpha over 2. It's now a t alpha. So that's the t in the equation from the first page. So let's look at number 2. Find the critical t-value that corresponds to 98% confidence. Assume 16 degrees of freedom. Now be careful. Level of confidence means the middle 98%, so we need to draw it and see what's actually to the right of my confidence interval. Okay, so we have our degrees of freedom, 16. 98% confidence interval means 0.98 is here. It means 2% is on the outside, so that's 1% on either side. So what's actually to the right of my critical value? It's actually only a 0.1. So across the top, we're looking for the t value of 0.01 to the right. So we're looking for 16 degrees of freedom across t of 0.01, and we should get a t value of 2.583. So if TC problems are important, just practice looking for them. So how can we use this to construct a confidence interval for mu? What you need is some sample data from a simple random sample. Sample size is usually pretty small, and the data has to be, data comes from a population that's normally distributed, or the sample size is large. Now, a 100% confidence or confidence interval for mu is x bar plus or minus our error, where our error is now calculated differently. It's now our t alpha over 2 times our standard deviation divided by the square root of n, where n is our sample size, where t alpha over 2 has to do with the confidence interval. It's just like up here. If we want a 98% confidence interval, that means we're missing 2%. Cut that 2 in half. The 0.02 is now 0.01 is what we're looking across on the top. And where t alpha over 2, that's the critical value with n minus 1 degrees of freedom. Okay, so in the next video, we'll actually walk through a problem from start to end using all of these things. And that should wrap up chapter 9.